I'm Erica Moody, the director of the Stat Lab of the CRM, and it is my greatest pleasure to introduce John Wakefield, Professor of Statistics and Biostatistics from the University of Washington. John is a winner of the Guy Medal in Bronze from the Royal Statistical Society. He's a fellow of the American Statistical Association and has written an excellent book called Bayesian and Frequentist Regression Methods, which I know at least the graduate students in biostatistics will be familiar with. We refer to it often in Bio 612. Now, John's well known for his work in ecological inference and spatial statistics, and has been focusing in recent years on small area estimation, work that is of great international importance. So we're excited to hear about your new work, John.
Great. Thanks, Erica. Thanks for that kind introduction and for inviting me. Yeah, and please ask questions as I go along if anything comes up. So yeah, this is work. I do have a lot of slides, so I'll some of them I'll do briefly, and then we can always go back to them if there are any questions. But yeah, this is work that I've been doing for probably 12 years now or something. I started looking into small area estimation in Washington State, but then for the last 7 years, probably I've been doing it more internationally. So this is the outline of where I'm going to go. I'm going to talk a bit about small area models generically, then I'll talk about child mortality, which is going to be the focus of the talk, and then talk about the specific models we've been using to estimate child mortality at subnational levels. So as motivation, many people who live in lower middle income countries do not have or aren't covered by civil registration and vital statistics systems. And so to get any information on health and population indicators in general, then you have to look to other sorts of data. So in particular, I'm going to focus today on these household surveys, but we also look at data from censuses as well. And I'm going to focus on this under 5 mortality risk. So the probability of dying before age 5, because it's a key indicator of the health of a nation, and there's targets that have been set to try and get it down to a certain level. And I'm going to talk about, so in the world in spatial statistics, admin 0 is the country level, and admin 1 is the next level lower, and then admin 2, 1 below that. So in the US, admin 1 is states and admin 2 is counties. And so there's different, so I'm going to focus on admin 2 estimation here, because those are in lower middle income countries, those are the level at which health interventions are made. So there are local health authorities at the admin 2 level, and so they're interested in their own, what's going on in their own regions, and then they can make suitable interventions. And also targets maybe, you know, if a new intervention is made, you might look at that at this admin 2 level to see whether you're lowering the risk or not. So just to place this in context, so the group I've worked with for quite a few years now, called the Intergroup Agency on Mortality and Estimation, so it's UN IGMI. So that is the group I've been working very closely on this work. And if you go to their website, which I've given here, or the website, and then there's this report, they every year they bring out estimates of the under 5 mortality rate. They do lots of things, but you know, they do neonatal, under 1 infant, various stillbirth rates. I'm involved in that also. And so they only do this at the national level at the moment, but just to place in context, I've just selected, it's not a random collection of countries. So here is what the under 5 mortality rate was estimated at in 2018. So the countries that are really good at this, so Japan and San Marino, I think, usually vie for the lowest. So they're about 2 deaths per 1,000. And then the highest, I believe the highest in this year was Somalia, certainly one of the highest. And Nigeria is also very high. So they're over 10% of kids who die within the first 5 years of life. And then we've got, Canada is around 5 deaths, UK is 4. I think they're actually very close. I think UK might be 4.3 and Canada is 4.6 or something like that. The US is slightly higher at 7. And then we've got a lot of the countries we'll be looking at, like Malawi, have the rate of about 50. So 5% of kids die. So I'm expressing these per 1,000 live births because that's the way people tend to interpret them in this world. And so I just wanted to give you some level to calibrate some of the numbers we'll see later. And so at the moment, the UN, for the last quite a few years now, have published annual under 5 mortality rates for every country in the world. And so the way the process works is, so there's this thing called the TAG, so the Technical Advisory Group, which is I'm a member of. That's about 10, 15 people who advise the UN on various things. And this is one is specifically for infant mortality. So twice a year we'll meet, and then we'll go through country by country, looking at the results, looking at the quality of the data and the different smoothing models they're using. And then on the basis of those discussions, we come up with estimates, and then those are sent to the countries to comment on. So that's called the country consultation. And then on the basis of that, they may know of other data sources or particular idiosyncrasies of the data that they think should be taken into account. And so on the basis of those, they come up with a revised set of estimates, and then those are published. And so this year, for any time now, well, probably within the next month, the UN will be publishing subnational estimates produced based on this work that I'm going to talk about now. So there's a whole host of people involved in this, which I've got a slide at the end with that. But that's the aim is to get as many countries subnational estimates for as many countries as we can.
Objective function kind of interchangeably, and you see this. If you look at other.
Sorry, can you say that again?
I specifically mean this thing. So objective maybe is with respect to all the data points at once, and loss is with specifically with one particular pair of input and target points. Okay. Just keep that in mind, because you'll.
Sorry, sorry, you're cutting out, so I couldn't hear all of that. Did you hear that, Erica? Or you could type the question. Sorry, I couldn't hear all of that. Sorry,
yeah, I couldn't catch it either. Perhaps you could put it in the chat. Thanks, John. You can go ahead for now.
Okay, thanks. Thanks, Erica. And so the General Assembly of the UN set some goals in 2015. So for by 2030, there was a whole bunch of these so-called sustainable development goals. And in particular, they wanted under 5 mortality to be below as 25 per 1,000 live births. So that relates to those previous figures I showed. And so many countries in the world are still way above that level. And then within the small print of this sustainable development goals, they talk about disaggregation by various things, including geographical location. So that's a big motivation for this work. But of course, it is important to know of variation within countries as well as the overall level. So you can focus endeavors have more targeted endeavors. And so just to talk a little bit more about the data we're going to use. So I'm going to focus on these household surveys, and all the stuff I'll talk about today is all going to be in terms of these demographic health surveys, which are this program has been around, I believe, since 1984, and hundreds of these surveys have been carried out. Nominally, they're carried out every 5 years, but that changes. And it's different in different countries, but they have, so the typical design is they use stratified two-stage cluster sampling. And so they'll on the basis, I'll talk a little bit more about that later, but they basically select households, and then the women in those houses, relevant to the work I'm doing, women between the ages of 15 and 49 who slept in the house the night before are asked detailed questions about their children, in particular when the birth dates of their children, and then if they died or what age they died. There's also information called summary birth history, which is, I've done a lot of work trying to disentangle signal from this, but it's very interesting data, and it's much more extensive than the full birth, so-called full birth history, where you get to know everything, because the summary birth history, they ask each mother in the census. Many censuses in low medium income countries ask mothers, how many children have you had and how many of them died? And so there's clearly information there, but you don't know any of the exposure times. You don't know when these children were born or died. So you have to apportion those deaths out over the births and deaths out. And so I've tried to I've analyzed data from these types of studies, but there's all sorts of subtle biases there that can go one way or the other. So at the moment, we don't use that data. The IGMI do in general, the UN do in general for their B3 for some countries, but we're a bit cautious about using that at the moment. So we haven't been using that data yet, though we may do in the future. And then there's very little vital registration. Most of the work I'm going to report is for African countries and sub-Saharan African countries in particular. And so this vital registration data, we haven't really got into using that too much yet, but there is interest in doing this for countries in Latin America, and there is pretty good VR data as well. So we're trying to, it's subject to bias, but I think there's a hope we can model those biases. So we plan to try and start incorporating that in the future. And so they, as I said, they use these stratified cluster designs. So of course, the big question is, do we use design-based or model-based inference? So I'll talk a little bit about pros and cons of those later. When we drill down to these lower levels of aggregation, so if the first lot of work we did it at the admin 2 level and 5-year estimation, and there the weighted estimates were quite reliable. And so we did a little bit of space-time smoothing, but not much was needed. But now we're going down to admin 2. Some of the areas don't even have any data. So you clearly have to, if you want to produce estimates, you have to do some smoothing. There's other idiosyncrasies of the data. So we don't get the exact coordinates of the clusters. They're jittered via there's a known algorithm, but there's some random errors or randomness is added to those points, different amounts in urban and rural. And so that's always a problem when you want to go down to really low levels. So we've looked at that a little bit as well. And then another open question is, what should we be displaying? So I'll show some ideas on that later. And so, as I mentioned, the UN IGME does these national estimates through this so-called B3 model. That's what is it? B-spline, Bayes, and bias corrected. And so that model smooths over different data sources over time and just produces national estimates only. So what we want to do is annual subnational estimates. And then we've got a bunch of questions that we'd like to address here. So, what sampling model should we use for the data? How do the UN want us to benchmark to the national estimate, so how we should do that, what kind of space-time smoothing models, and then how we account for the design as well. I'm going to talk a bit about that today. And then, I've got a slide later if anybody baits me into doing it, but there's another well-known institution in Seattle that produces subnational estimates, but I have views on their methodology, which I could pontificate on in an extra slide. But suffice to say at the moment that we're focusing on having transparent models and reproducible results. So we've got software that we've written packages for this work. And so if you input the data, the DHS data, if you download that from their website and you input it, you will get exactly the same answers as we do. And so that is important. So just to give you an example of what the data look like. So here's in Kenya so we want to construct these undefined mortality estimates over a range of years. So from 1990, specifically 1990 through to whenever the last survey was, then forecast forward to 2019. And so for this period in Kenya, there were 3 DHSs in 2003, 8, and 14. And they used stratified 2-stage cluster sampling. In the first couple of these surveys, they used 8 provinces crossed with urban rural, and then the last one they used 47 counties crossed by urban rural. That was a much bigger one. There were I think there was about 400 clusters for the first 2, and then about 1,600 for the third one. And then they sample. So then there's a partition. The sampling frame is these enumeration areas, and they randomly sample within each of these strata. First they sample the enumeration areas, then they sample households, and there's typically 20 to 30 households are sampled in each of the clusters. And then, as I said, all women are interviewed, and then lots of information. These interviews take like 4 hours. So there's much information. And the DHS brings out reports after, whatever, 6 months after the data finalized, they bring out reports. These are big 300-page reports on all sorts of demographic outcomes. And then the way the DHS does it is they use it all through design-based inference. So they give design weights to account for. It's actually PPS as well, sampling they use, and then they do some response adjust non-response, but the response rates are pretty good in the DHS. So this just shows you a picture of what for Kenya the 3 surveys. So these dots are very small, but so there's Kenya with the eight areas on this side and 47 on this side, and so we see the maybe you can just see there's more blue dots. The blue surveys were about 4 times as large as the previous 2 surveys. And then one very interesting aspect of this work is that, so if a woman, so this is for the 2014 survey, what I'm shading here is births. So the number of births, so this goes up to about 1,000. So in these darker areas there was about 1,000 births reported in this 5-year period. So a woman who's 49 and interviewed, she could have had a baby when she was 15. And then so she's telling you something about, do the math, 34 years earlier. So these gray areas where we have no data, and then these, the dashed areas or the hatched areas are where we have very little data. So you see, as we go through time from this survey, we gain more and more information. So the last 2 time periods, we have quite a lot of data because we have the full range of mothers. So we've got this weird sliding scale of mothers mothers' ages that are being used to construct the estimates. And that's a problem because, of course, the probability a child dies is a function of the mother's ages also. So we have this U-shaped distribution. So some of the children, I mean, some countries like I was in Malawi when October of the year before last, and there's children there at 13. That's not rare for 13-year-old children to be giving birth, and the health outcomes of the mothers and the children is much poorer than older women, and that's the end age groups is the same as well. And of course we have these overlapping surveys. So the 2008 will inform on the 2008 period, and then less as it goes through time. So we try and combine all these surveys into estimates for each year. So here, so these are the 22 countries we considered. So we've been quite, the UN in general are quite conservative, and we're following them in that we're only analysing the countries that we feel we can do a good job with the methods we currently have available. So in Benin, for example, there are three surveys, 3 DHS were carried out in the relevant period. There's 12 admin 1 areas and 76 admin 2. You'll notice that we don't always analyse the admin 2 areas. So for example, the poster child for being a difficult country to analyse is Nigeria, because there's 37 states at the admin 1, but I think there's 776 admin 2 areas. And so that's a huge number. So, and about a third of those don't contain any clusters in the latest DHS. So it's difficult to make. We've made estimates of those, but we don't trust them enough yet to have them published. So these are the 22 countries. You can see, like Senegal has lots of DHS. They're one of the few countries that has the so-called rolling DHS, where they keep collecting data every year. So, or most years over recent periods. So this is one of the difficulties, that every country has got its own rules for doing things, and the geographies change over time. Ethiopia uses a different calendar that threw us for a while, and so every country there's something we had to do differently. So like Myanmar, there was a cyclone back in 2008, so we need to do a crisis adjustment. The same thing for Rwanda because of the genocide. So this is one of the reasons we do things country by country. And I say we've analysed way more countries than this, but these are the ones we feel we have reliable estimates for. And then this is the spoiler alert. So here's the answers. So admin 1, these are the countries that we've looked at. So we can see like Mali has got quite high levels. Northern Nigeria has also, that's true of many health outcomes. Sierra Leone and Liberia, these are predictions for 2019. And you see we've got good coverage on East Africa and Southern Africa, but less. When one of the aims is to improve this as time goes on. And these are our forecasts for what if we oversample some areas but ignore them when estimating. Right. So yeah, we have to adjust. So we have to adjust for the stratification. So the model-based approaches we use, we put fixed effects in for the strata as much as we can. I'm going to get onto that. There's difficulties with urban rural, but we have effects for each of the areas at which the sampling was carried out. So that's going to adjust for at least the oversampling in those areas. Does that answer the question? Okay. So small area. So there's, for a generic prevalence P, that we can think of design or model-based approaches. And so under the design-based approach, the labels of the area, the clusters that were sampled are the random things, and the responses are treated as fixed, and then we can use asymptotic inference. And so our early work, we did use the sampling weights are constant within each. Well, that's a complicated issue. The sampling weights should be constant within each of the strata, but they make some adjustments. Okay, so the DHS, the way they do things is they have a sampling frame, but then when they go to a village, they adjust the sampling frame. So in a census, they'll normally know how many households were there, but then when the the people doing the surveys go to the villages or the enumeration areas, they'll draw a map, an updated map of where all the new households are, and then they'll do the randomization. So that will change the the number which are selected within each of those, the number of, so the weights change then because you haven't got the same number of households that you thought you had originally. So there are some changes in the sampling weights, and that's actually can be quite considerable. So model-based inference, you condition on the units that sample to treat the responses as random, and then you can carry exact up to your model being correct, exact inference is going to take place. So the way I think about this, there's 3 ways you can do small area estimation. So you can, in the perfect situation, if you've got a load of data, you just use the weighted estimates. That's great. And so, for example, if I'm doing Malawi in a 5-year period, Malawi had a really big survey, I would definitely use just direct estimates to do this. We've got large numbers, so the asymptotics are fine. The work we did for 35 countries, we use what I called smooth direct. So the direct estimates are these where you just use the data from those areas only, the response data. Smooth direct, we use that in the situation where you've got, actually have a little picture here. So sufficient data at the required admin long, go with direct estimation. If you don't, then if you've got a good variance estimate, then you can use this smooth direct. So that's basically saying, we've got a variance estimate, but there's quite a lot of uncertainty there. So I'm going to use smoothing, space-time smoothing, to try and use all the areas to get me lowered, increase the precision. And then finally, if we've got if you get, no sampling, of course, is the limiting case, but sometimes you might only see one or no deaths in an area, in a particular strata rather, in a time period, then you can't, then the variance estimates go belly up. And although there's some fixes around, which you could do if you just had a couple of areas like that, that's fine. But if you've got a third of your areas are messed up, then you don't want to be, doing semi-arbitrary things. So then we model at the cluster level. So then the models I'm going to talk about are going to be models at the cluster level. So we're going to take the data, basically we're going to take a binomial response at each of the villages or the enumeration areas, and then we're going to adjust for the design by putting in fixed effects for each of the strata, and then we're going to have a common random effect for people within this, for kids within the same cluster. So that induces dependence, which is going to account for the clustering, at least to some extent. Okay, so this is a little bit history of how I got into this. So 2016, I've been doing this small area work for about 5 years, just locally. Then I got invited to the UN IGMI meeting. And then over the next 3 years, as I said, they're quite conservative. They're a mixed group of like demographers, epidemiologists, health policy people, public health. And so, they're very cautious about models, which is fine. I get it. And so, over the years, I was developing these models with a ton of other people. And so the models evolved as a function of their questioning. And then finally, I convinced them that we could go for this. And so we first did these 35. These weren't the official UN figures, but these were they endorsed them. So that was a paper that came out last year, but it took us like 3 years to produce these estimates. Then I joined this technical advisory group, so that helped things. And then this was very good. This helped me a lot. So in 2019, I went to 3 workshops in Ecuador, South Africa, and Malawi, and that helped a lot to meet the people who are actually collecting the data, and the national statistics offices basically were the people that were there from these conferences or workshops. And so then we developed a Shiny app to get them to do these things themselves, and that was great for just getting the local context. And then finally then IGMI said, okay, can you come up with admin 2 estimates? And so that's what we've been doing over the last year and a half, and those are the things that are that map I showed earlier, that's going to be appearing on the UN website sometime in the next month. This just shows how the methods went. We started very simply with these smooth direct things. So they're basically Fay-Harriot models. For those of you who know these things, it's just a particular space-time version of those. And then we went through just comparing continuous and discrete spatial models, adjustments for the design. So this paper came out within the last couple of months. So this was, just showing how we could recover the weighted analyses if we were careful about how we did the adjustments. As I said, we looked at summary birth history data and decided that it's not ready for prime time yet. One of the problems is the data sometimes, there's this jittering part, but also some of the older surveys don't actually tell you where the cluster is. They don't even have a jittered location. They just tell you which administrative region. And so, So my favorite paper title is in here. So one, you know, as you get old, you start caring less. So when we're using area data only, I got a paper called Pointless Spatial Statistics. So that's because we only have areas and we reconstruct a continuous surface. And then we started using these over dispersed binomial models. And so that's what I'm going to talk about today. And then I thought quite a lot about how to visualize the results. And then this summer package is, I mean, Richard Lee has done a huge amount of work with both methods development and computation. So we've got this package, which means we can do all the computation pretty quickly. So we don't use MCMC, we use this in-law methodology. And so that makes things relatively quick. I mean, it takes, to do all the countries, the data processing takes quite a long time because you need to download all these births and deaths and get them into a certain format. That takes a while, probably more than the analyses themselves. But any one country will take, you know, minutes rather than, you know, it's small countries will be very quick. So here's the weighted estimator so I denotes area here and T is year. That's what I'm going to talk about. And so we've got this asymptotic distribution, and then we can basically smooth PIT using a space-time smoothing model. That's the basic idea for smooth direct. The cluster-based models, again, just for a symbol binary response, of course, we don't have that because we need to consider death at different ages. So I'll get onto that later, but this is the starting model. So we have this binomial model. So we have a number of children who were born and then a number who die, and then some probability of that. So the probability of that occurring. So this now is cluster C within area I in year T. So we have random effects. So yeah, so the variance, so it's a very different approach. So rather than having those, you know, those beautiful formulas that survey samplers come up with what we do is we have this shared random effect, and so that induces dependence in any children born within this cluster in this year will have this shared random effect, and so that induces dependence between the observations. The other way we're going to do that is via a beta binomial distribution, because it basically induces over dispersion. I think I've got all of that. So now this is where the real hassle starts. So we're modeling these clusters, but we actually want the area. So we have some area we want to make an estimate for. We sample some clusters, some of which may be urban and some of which may be rural. And so when we want to get the summary for area I in year T, we need to take the prevalence at each point level and then aggregate it with respect to population density to come over the area AI. So we've got these two surfaces. We've got a population surface, which of course we have to estimate because it's not known. We never know the sampling frames here. We never know we might know the sizes, but we never know what the constituents. We probably don't even know how many enumeration areas are in each of the admin 2 areas. Then we have a density. So we average those two things together. Then we can split that into two, the urban part of the integral and the rural part of the integral. So this is a big pain. So having an area level model where you can directly model that is great if you can do it, but unfortunately we can't always do that. So this is one of the reasons that when we assume we're going to use spatial models, which are discrete spatial models. So although continuous spatial models are more theoretically, they're much nicer things to, you know, they allow you to carve up space in any way you like. You can combine data with different geographies, but so, you know, some areas, you know, over time, the admin boundaries might change. So you can, if you've got a common surface to splice up, you can very coherently do that, which isn't true of discrete spatial models. But you've got this big problem that when you do the aggregation, you need to average out. Whereas if we have a discrete spatial random effect that's constant within each area, then we can do the integration quite easily because it's constant within an urban and a rural, we can just take the proportion of the area that's, which way around is this, urban, and then this is the proportion that's rural, and then just take, we've got an urban rate of undefined mortality, a rural rate in the area, and we just take the weighted combination of the two. So that's one of the main reasons we go with a discrete spatial models. But even so, we still need to get at these RITs, which is the proportion of an area that is rural, area I that's rural in time t. So this is quite recent work that I'll report briefly on. we've been trying to do this. We've come up with an urban-rural classification model. So the reason we're doing this is because they stratify by urban-rural. They tend to oversample urban areas because most of these countries, the majority of the area, like Malawi, is over 80% rural. So they oversample the urban parts of those because they want to make sure they have enough samples there so they can characterize urban risk in those regions. And of course, nearly everything has got a different characteristics in urban rural areas. So in general, urban risk of death in the first 5 years of life is lower in urban areas than in rural areas. So if we don't adjust for the urban rural sampling, oversampling, we will underestimate risk because we'll be putting too much weight on the urban clusters, which were oversampled. So what we do is, the way I think about this, we have this mortality model at the cluster level, then we have an urban rural classification model, and then through this equation here, we just put them together to come up with our aggregated estimates. So this is just showing how the conceptually, you know, so we could have a continuous spatial model like this, or we could model it discrete. Bless you. And so, yeah, currently we use this discrete BYM model. I'm not going to go into this. It's just a particular conditional autoregression model. I could talk more if people want to. So here's some horrendous notation, which I'll very quickly go through. But we're going to be smoothing over year and over space, the clusters within space. We have multiple surveys here, which I'm going to index by K. We also have multiple age bands we're going to model at because child mortality is highly dependent on when you were born. On your age. So first month of life is the most dangerous by far. So roughly, on average across the stuff we've looked at, if a child dies within the first 5 years of their life, there's 50% chance they die during the first month. And so what we need to model this, the probabilities of death at each of the ages of the child's age, and then from those we can come up with the undefined mortality. And we also, another complication is we've got different sampling frames in different surveys. So for Malawi, there were 4 surveys we used, and there's 2 different sampling frames because there was censuses in 98 and 2008. And so 2 surveys were constructed with 1 sampling frame and 2 with the other. And so we need to do different amounts we need to model the urban rural effects differently because they're defined in different ways. So this is all detail, which I'm not going to go into. This just gives you some idea of these 4 surveys the DHS did in Malawi. So this is the total number of clusters. So they're 500, 500, 800, 800 roughly over these 4 surveys. This is the percentage that were urban. So in the 2 censuses, 98 and 2008, around 15% of the population was characterized as urban, but you see this oversampling in all but 1. 2004, for some reason, they undersampled, but the other 3, they oversampled. So we want to have survey-specific adjustments for urban rural. So that's what we do. I won't talk about the details here, but so in the 90s in particular, there was a huge bias because mothers who died from HIV obviously wouldn't appear in the surveys, and those mothers their children were allowed to, their children had a much higher chance of dying because they you know, for all sorts of reasons, the obvious one being they were infected with HIV, but also, you know, losing a mother, you know, for all those reasons, there are very big, basically we've got very highly informative missingness. So these just shows you these are for Kenya, these are the adjustments we had to make. So roughly speaking, we have to bump up all our estimates by quite a lot so this is the worst problem is in the 90s. And then when, you know, the treatment started coming in, you know, in the early noughties, then this became less of a problem. So these are the adjustments we need to make for the 3 different surveys. So again, I could talk about that more, but I won't go into it now because it's quite involved. So in terms of the survival model, we're going to use a discrete survival model at the monthly stage. So we've got 60 months in which death could have occurred, month 0, i.e. 0 to 1, etc., up to 59. And so it should be like that actually. So the probability of dying in the first 60 months of life is 1 minus the probability of surviving. The probability of surviving is surviving each of the months conditionally. So we basically have the classic hazards. You know, you survive in the first month, then you can survive in the first month, given you survived surviving in the second month, given you survived you were alive at the start of that month. So that's a hazard, a discrete hazard we're going to model. So we've got these hazards. The demographers have this lovely notation. So 60Q0 means death in the first 60 months. No, I didn't. I don't. Maybe somebody else did, but just to answer the question in the chat, no, I haven't done any work in European countries. So the probability of this is death in the first 5 years of life, and this is for area I and survey S at time t. And so, you know, the probability of, oops, sorry, that should be 1 minus. The probability of dying is 1 minus the probability of survival. And so what we do is we have a model for 0 to 1, a model for 1 to 12, and then a model for 13 through 24, etc. So we have 6 different hazards. So they look like this basically. So we get this is we want to estimate. So we have a constant hazard with months 2 through 12. So it's the usual trade-off. We want to have enough parameters to capture this shape of the function, but not too many because we don't have we don't have huge amounts of data. And so the way we can do this, the initial work we did, we used the good old weighted logistic regression. And so basically we get the direct estimates can just use weighting methods. That's all fine. You can get the variances from the delta method. So you just turn the handle and do all that. More recently, we've been using a model-based approach because, as I mentioned, the weighted estimation goes belly up when you go too far down because you don't have enough samples. So we don't actually use the jackknife. We use the delta method. We messed around with the jackknife and we basically got the same answer. So there's a particular, yes. So yeah, so the jackknife is specific to the survey. So you have to, the way you implement the jackknife has to be consistent with the way the survey was developed. So there's a way of doing the jackknife which respects the stratification. Okay. So yeah, as I mentioned, you can go area-based route or area level or unit level. We're going to go the unit level route. And so here we go. So you've got to keep your kids happy. So with your research, so the UN's model was called B3. So we needed a name. I was at Imperial for 9 years. So as Dave once famously said, it taught me how to market myself. They're good at that. So BB8, you've got to have a name. So BB8, doesn't that sound so much better than B3? So BB8 is a completely contrived name because we use a beta binomial distribution. And we do account for all these things, but if Star Wars had called it BB7 or BB12, we could have done that as well. So all these things we do, we benchmark, we do HIV adjustments, use Bayesian inference, we've got reproducibility in summer. So anyway, so BB8, that's the future. So here's the model we use. So there's tons of stuff on here, but I'm going to try and explain intuitively what we're doing. So the basic unit of modeling, we have an at-risk bunch of kids in each monthly age band. So we have a monthly age band in cluster C in survey K in year T. And so then there's a hazard that each of those kids could die. That if they enter they're in the risk set at that point, what's the probability they're going to die within the next month? And then we model that, the logit of that. We've got bias adjustment for HIV in a benchmarking term. Then we have an intercept, which depends on the child's age in months. So we have 6 of those, 6 urban and 6 rural. And then we have fixed effects for survey effects. We have a IID in time. We have 2 time series. We have 2 random walk models so that over time we get smoothly evolving trajectories. And we model those so that the different age groups, the way we do that, we have 3, again, because we don't want the model to be too complicated, we have 3 age bands. We model the 0 to 1s over time, the 1 through 12, and then 12 through 60. And then we have a spatial model, and then we have a space-time term. So just to show you a picture, this is for Malawi, the time trend. So this is hazards, but we've stretched out the scale. So the solid lines here are the rural areas, and the dashed lines are the urban. So in general, you can see the rural. So that particular age band. So this is the 1 to 12. So this is the neonatal. So they have the highest risk, and so this is over time. And so we're investigating Malawi at the moment. This looks real. We've been in touch with people at I know people from when I visited there, and they're seeing this as well. It seems to be that the neonatal rate of deaths is on the increase in urban areas, and they don't know why, and we can't see why either. But this is it's clearly the highest, and then so this is the 1 to 11 month death. So again, here we see, and the rest of these have all got distance. You know, the always rural is always above the urban. So what we have here is we have 3 random walks over time, 1 for this group, 1 for this group, and then 1 for the rest. And then, but we have 6 different intercepts. Well, 12 different intercepts, 6 by 2, urban, rural, and then urban, rural, and then 1 for each of the 6 age bands. And so anyway, this just talks about the smoothing models. We use a random walk 2. So random walk 2s basically say that you're penalizing slopes. You want a constant, the data are being pulled towards a constant slope over time. So any deviations between slopes in adjacent periods are being penalized. So the further the slopes differ from each other, we're penalizing more. So we're pulling towards a central curve. So on the logistic scale, we're saying there's a temporal, it's linear in time, but we're allowing fluctuations between different years. And then we have an AR1 interaction term. So the AR1, when we try to use random walks, so we have this interaction between the spatial model. So we have a spatial pattern, and then we have then that pattern evolves over time according to an AR1. When we tried a random walk 2, we got the random walk 2. For those of you who are into these things, that's an improper model, so it can be quite unpredictable. So particularly when we're forecasting, we wanted something that was a little less, could do wild predictions, so we went with the AR1. So this basically over time dampens things down, so things just go towards that common curve as we increase in time. And then basically that's the space-time smoothing is because you've got this this precision or inverse precision matrix encodes the neighborhood structure, and so pulls adjacent curves to be close to each other. Areas that are close to each other tend to have similar interaction terms. Then we do due diligence on the prize as well. So we're careful about how we specify the prize on the variance components. So when we've done all that, what do we do? Well, so now we get an undefined mortality. This is exactly the formula I showed you earlier, but now we have to pick up the specific intercepts for each age band, the temporal trends, and the spatial and space-time interactions. We have 1 of these each for urban and rural, and then we combine them by estimating these fractions of urban and rural. And then I won't go into the benchmark, but then we benchmark to the UN. So just quickly talk about this classification model. So the classification is really tricky here because, it's actually incredibly involved. When the sampling frame is formed, every cluster is assigned to be urban or rural, and then that's the way then the samples are. Then they do the randomly select clusters. But then when they go off, like they might use the same sampling frame like 8 years later when they do a new survey. Some of those clusters which were labeled as rural may well have become urban, but they don't change the classification. So in Africa in particular, there's huge urbanization going on. And so, quite a significant number of the clusters that are being labeled as rural aren't really rural, they're urban. So what that means is, the way I think about this, I don't think of it as urban rural. I think there's just some A-B partition in space that goes on at the time of the sampling frame. And then you've got to adjust for that because of the potential, because of the oversampling and the differences in mortality between urban and rural. You do need to account for it. So you need an association parameter in there, but we make the association parameter change over time. And we also don't think of it as an urban rural classification because it's not really, because that classification is diluting over time. And plus urban rural associations are changing over time anyway. So, and that's what we found that we see strong urban rural differentials, but they get, as you get further away from the sampling frame formation, they tend to attenuate because the things it's like a measurement error problem. The things you're calling rural are no longer rural in many cases. So what we've done is we take the clusters and we go for, we've actually been using gradient boosting trees to, we do the usual thing, remove some of the data, then train the algorithm. So it means this is a pure classification problem. We're trying to classify across a grid every point as being urban and rural. So we have these there's all sorts of surfaces you can use. So this is log of nighttime lights. This is log population density. These are both for Malawi. So we use these plus other covariates. We do a classification algorithm, and then we get classifications of it. We get an urban rural surface, and then we roll that out over time, assigning density to get the proportion of each area that is urban and rural. So that's the algorithm we're currently using. When we first did it, we found that the urban classification rates were quite poor. And we think, well, a large part of that is because of the jittering. So points which are, you know, your urban rural, for urban rurals in particular, where you've got, you know, being jittered by 1.5 kilometers is actually quite a big deal. That could easily put you into a rural area. So what we do is we do some pre-processing. So when we do this operation, this just shows under different approaches how the urban rural fraction changes. So we're estimating the proportion of people who are in, or the proportion of 0 to 5 population who live in urban areas. We need that to do the weighting. And this just shows you in a map how this varies. So for example, this is Blantyre. So Blantyre is where I gave this workshop. The capital is Longwy, so we visited there also. So those are the two areas which have larger urban populations. Everywhere else is pretty small. And this just shows, so these are the 28 estimates, depending on which weighting schemes we use. So if we ignore the stratification, still good and bad. You know, if we spend a lot of time sorting out the stratification, but it actually doesn't make a large difference. So if you look carefully, you can see the stratified estimates are slightly higher. They're above the line. So what I've plotted here is the unstratified versus the stratified estimates, and we see a slight increase because to account for the oversampling, but it's not a great deal. That was at admin 1. This is at admin 2. So final things I want to say is just how we, you know, report the results. So one thing we do is we show these so-called spaghetti plots. So these are for Malawi, the 28 areas of Malawi. These are the under 5 estimates. So back in 1990, you know, there was very high late, 20 to 30% of kids were dying before their 5th birthday, and now it's down. You know, we're around what here now. The last survey was here, so they're down to like 5% now. So you know, it's still larger than, it's still 10 times bigger than it is in. You know, we know from those figures I showed earlier, we know we can get this really low. This is all preventable, you know, or almost. You know, if San Marino and Norway have 2 out of 1,000, why can't everywhere? This just shows. So dark here is better, maybe not the best color schemes here. So early on, we see these areas with very high rates in particular. So this is just in the last 10 years, and then it drops. So there's much. So the variation is dropping a lot. So the level is dropping a lot, but there's still quite considerable. If you look relatively, there's still quite a lot of variation across basically all the countries we look at. This is a map which what we were trying to get at here. This is work with Tracy Dong, and we in her thesis we tried to think of a way we could portray uncertainty and the estimate size on the same map. So what we said is, suppose so every time, you know, when you see a map with full colors on there, you think, oh, this is the truth, right? But of course, at every point there's uncertainty. And so you could imagine splitting into different color coding. So here we've said, here's 2 colors, but beneath each of these colors, maybe I'll show you this. So here's one way we can look at these things. These are called Ridgeplots. So these on each row here, each row within each panel, there's 28 posterior distributions. They reflect what we believe about the under 5 mortality in each of those 28 regions here in 2014, here in 2020. So there's uncertainty. And then when we do a map, what we do is we just pick a point, the median of these, say, and then we assign it a color. But of course, there's massive uncertainty. So what we do is we've been thinking about just putting a limited number of colors. So if I have 2 colors, then this ATCP is the average true classification probability. So that means if I randomly pick an area here, there's a 77% chance that it's in the right box. So that's not that great, right? And if I went to 3 colors, it might be 50%. So there's a trade-off here about how many colors we have, because the more colors you have, it means you get more fidelity and you can see more signal, or so you think. But there's also more chance that you're deceived by it. So what we're trying to do here is come up with a plot where we implicitly can see how much. This tells us, okay, you know, there's only 2 colors here. That means there's a lot of uncertainty still. So these are the sort of things we've been looking at lately. So yeah, just to finish off, So here's the countries we've currently done. You saw the answers earlier. This is an ongoing thing. So we're thinking still more about the stratification, in particular, how we do the classification better. We're looking at better ways of doing benchmarking. There's all sorts of these selection biases we're looking at, like age heaping and modeling mother's age. We need to consider gender as well for the kids. Migration, some of these women who were interviewed may have lived in a different country 30 years ago. So we want to look at the impact of that. We'd like to try and bring in summary birth history and vital registration data in order to be able to expand the country list. So as the models get better, we hope we can bring in more countries. I didn't talk much about assessing model adequacy, well, nothing. I didn't say anything about model adequacy. What we tend to do is, as a minimum, we predict at the admin 1 area and see if the estimates we get are consistent with the weighted estimates. Yes, I'll get onto that. Yes. So yeah, ranking, that's another thing we do. Yeah, I haven't got any pictures here, but yes, we also produce ranking plots. And yes, the ranking, when you look at rankings, because you're doing this as we simulate. We use INLAR, but then we simulate from the posterior in order to do the aggregation. So we get samples from the posterior. So then you can, for all your 28 areas, you can rank the samples and come up with the posterior distribution that this is the first or the second. And yes, if you want to rank them, it's very, very difficult to do that. And that's another way of showing the uncertainty. Yeah, there's still huge uncertainty in each area, basically. Yeah, so I mean, we want to be able to. The reason we do this is the summer package, and we try and look at even more efficient implementations because we want the countries to be able to do these estimates themselves. So when I've given these workshops, we have this shiny app which does very simple forms of the model, but we need to improve that. What else? We're trying to make conflict adjustments in a better way. So those areas which have like civil wars going on, can we make adjustments to that in a better way? I mean, yeah, down the road, it's not clear when we're going to be. From what's known now, maybe not many kids are directly dying from COVID in low middle income countries, but in terms of stalling of vaccination programs, there's definitely going to be an impact of that. So trying to pick that up is going to be really important, but really difficult. And finally, we've been trying to get into cause-specific mortality. So some of the surveys have information. It's not very high quality data, but we have data on cause of death. And so, yeah, just make the obvious point at the end, that substantively, U5MR, under 5 mortality is dropping in most low middle income countries, but it's still way above the SDG target, and there's still very high within country variation. So yeah, thank you. That's all I had to say.
Thanks very much, John. We have, maybe John will be willing to stick around for a little while, but even
sure.
If not, we have some time for questions if there are any for our speaker. Well, John, maybe I'll jump in. Could you talk a bit about how you do the conflict adjustments now and what you think is lacking or needing further issues? It sounds really interesting.
Yeah, we don't do it in a very, the problem is we don't have subnational information. So the 2 countries out of those 22 we had to do a conflict adjustment for were Rwanda and, excuse me, Rwanda and Myanmar. So in Rwanda, so there are databases around which estimate the number of children who died during the genocide. And so what we do is the way the UN does this, they make a one-off adjustment to the total. They add a number of deaths in the numerator, basically, and do that at the national level. What we just do is we apportion it due to population in each of the subsequent areas. So we need to, literally today I've been talking to the UN about better ways of doing that by getting some subnational information. Myanmar was different because that was this, I think it was a tsunami that came in and devastated all these, in 2008, all these coastal regions. And so this is one, so I have to take a free shot here. So the IHME do under 5 mortality, and they did a constant adjustment across the whole of the country. And so we know we have an estimated number of children. So what we did, we just made that adjustment because IHME do every country in the world. They basically, they can't, and they're doing every cause of death in the world as well. So, I just do under 5 mortality in 22 countries, so I can take a bit more time on it. And so what we did is we looked into it and found reports of which areas were most hit. And so the coastal regions, we basically assigned all the deaths to those coastal regions, again, of course, according to population. But the problem is we just don't have enough local information on the on where the deaths occurred. We want to do it in Liberia and Sierra Leone as well, because there's been civil wars there, and we need to try and do something there. But at the moment, we just don't have the information.
And John, I see there's another question in the chat that I'll just read to you. It says the ridge plots show substantial overlap. It seems one can't really differentiate or rank the regions due to the variability. And I was asking if you had any comments or thoughts on that.
Yeah, so we yeah, so I don't have probably don't have, do I have them lying around on this computer anywhere? Yeah, so we do look at the ranks, and you're right, they do show huge amounts of, oh dear. Just see if I've got a previous talk where I've got a picture on that because what am I looking for? Quick look here, see if there's any. No. Yeah, so yeah, if you look at the ranks, you do see there's huge overlaps in the distributions, and so yeah, I mean that's another way of reflecting uncertainty. But yes, there is huge uncertainty. You might be able to say, yeah, this area is definitely in the top two, and this one is definitely in the worst, you know, in the worst two. But beyond that, most areas it's very difficult. In many of the cases, are very difficult to discriminate between. Just keep looking to see if there is a picture anywhere of the rankings. No, I don't think I've got any, I'm afraid.
Okay, thanks a lot, John. I'll just open the floor and see if there are any other final questions. John, there's one in the chat. How do you deal with spatial dependence when you see variation in rates across an area to study area, the variation of which could be due to an exposure with which you want to understand? So are you doing any regression, understanding exposure?
No, we're not, no. And that's, yeah, no, we've been kind of wary about covariate modeling at the moment. So I'm not sure this will answer the question, but we've so if you're doing area level modeling, putting in area level covariates, we've tried a bit of that, and that's okay. We've put in things on child mortality and we've put in things on mother's education level. So average mother's education level within the area, and also malaria prevalence. Those two are somewhat helpful. Well, helpful in the sense that they come out as significant associations, but actually in terms of improvements in predictions, they don't really improve on the space-time model. It just means you're apportioning in different ways. The problem with the models we're using is that we have all this. It's very frustrating because we have all this very detailed cluster level information. So we know lots about the children, the mothers, the villages, you know, but then if you want to aggregate to get small area estimates, you need to know all that information for every cluster within each of the things you want to aggregate over, and that data just isn't available. So we've been kind of cautious about doing covariate level modeling. But yeah, then of course that is the important, that it's not just characterizing where's high and where's low. We want to know why those areas are high and low. At the moment, we just do that anecdotally through our, you know, reading up on countries and understanding, you know, like Kenya in the southwest, it's very high rates, and that's, you know, there's malaria there, there's high HIV, there was high HIV historically, and it's very poor. And so, but beyond that, no, we haven't got into associations too much lately. Not for small area estimation anyway. We've done this just at the cluster level, but never for small areas.
Presumably you'd have the additional uncertainty of ecological inference then too, because it's
yes, right, the area level modeling, yeah, definitely, yes.
Right. Well, we're up to the 4:30 now, so I think we'll stop and thank you now, John. Maybe John can stick around for one or two questions, but
sure, yeah,
we can all thank John. We'll give you a virtual applause.